So now after the introduction, I turn to the original goal. So since I thought that we know everything about cohomology classes, I was interested in CSM classes because using CSM classes, you can calculate the Euler characteristics of these varieties of tangent lines. And I'm glad Richard mentioned that this is a baby example. I think in a sense, really this is the simplest, one of the simplest applications of this theory. And I really wanted to have like one example worked out to the details. So then for more complicated applications, you can just use the pattern what you learned. Okay, so as I mentioned, this covering can be used to calculate CSM classes, and the corresponding theorem gets a little bit more complicated. So it's a very similar formula, at least the first part is kind of similar. Okay, so you have this smaller partition, and you make this funny substitution, and you multiply with something which looks like an Euler class. Okay, so this product is like the Euler class of something, and you have this extra part, which is like the Chern class of a line bundle, if you wish. But you have a bunch of other terms. And this is what we expect when we work with CSM classes. We have to take it seriously that whether we work with a closed variety or just the stratum itself. And as in almost always for the CSM classes, you have to take care of the more complicated strata in this case. So the point is that if I go back to this covering, then the image of this phi, the image contains a lot of strata, a lot of new strata. So this is what is collected here. So I have to subtract the CSM class of these more complicated strata. This V here refers to the notion of fusion. Basically, I wrote down an example here. It's very simple. You take the highest multiplicity or highest part, if you wish, and you can fuse it to any other parts. So like the first partition is given by, so it's always 5 what I glue to another number. Here I glue to 5, here to 3, and here to 7. Okay, so this is how you get this formula. Now, the nice thing about this formula that this allows us to calculate inductively if you use the fact that cohomology is a graded object. Okay, so if you don't want to calculate a full CSM class, only one graded piece, then it turns out that you can organize the induction that for these partitions in the fusion set, you already know what you need, either because it's 0 or something that's much more simpler. Okay, so I don't want to get into the details. What is important is that the same way as we proved the polynomiality for the cohomology class, by induction here you can also prove that even these coefficients of the CSM classes are polynomials. But there is one little problem at the beginning, that you have to start. And to start, you have to study the Chern classes or CSM classes, it's the same, it doesn't matter, of the whole space. And I was 100% sure that this is well known, but apparently it's not, and probably it's not an accident that these are not known. I cannot give you a closed formula for these classes. So maybe just to compare, uh, so there is another uh, problem when you take the same, oops, sorry. Uh, just you replace D and 2. So if you want to calculate CK of all to CD, then these are very famous formulas of Laszlo, uh, Lakshov, I hope my pronunciation is correct, and Toru. Okay, not entirely simple. The coefficients are determinants of binomial coefficients, but at least there is a closed formula. But this one is much more complicated. And in fact, we needed to develop, okay, so maybe before I go on, so let's see what is this object we want to understand. So what is the Chern class of all these C2? Well, it's a giant product of all the weights. Okay, so you have to multiply 1 plus IA plus D minus IB. Okay, there is an equality missing here. So at first, it looks very innocent. Of course, after you multiply them, you want to understand how you express this. This is a symmetric polynomial in A and B. So you would like to see in terms of some basis of the symmetric polynomials. And it's extremely difficult. So we developed a theory with András Juhász. What he came up with this name, I really like it, the theory of rising products. So let me just give a theorem here. So what is a rising product? You take a polynomial with 3 different types of variables. Oops. Here is this polynomial. Okay. And you take the product where you substitute into I the arithmetic sequence 1 to D. Okay, and the key theorem of this theory is that the coefficients, for example, in the monomials, which would be the same as saying that in the monomial symmetric basis are polynomials in D. So just see how non-trivial problems can come up. I show you one example. Okay, so let's say that our polynomial is, sorry, yes, 1 plus ix. So there is not even a dependence on D. Of course, in the product, there will be a dependence on D. So then the coefficients there is only one x variable here. So in general, you can have many x variables. Here you have only one, and it turns out that the coefficients are the Stirling numbers of first kind. So one definition of these Stirling numbers is that you take the elementary symmetric polynomial and you use this substitution. I coined the name arithmetic specialization because it's kind of similar to the principal specialization. So instead of a geometric sequence, you write in an arithmetic sequence. So these numbers come up everywhere. For example, if you think of the binomial coefficients as polynomials, then the Stirling numbers are essentially the coefficients of these polynomials, but you have to manipulate it a little bit. So there is the defining recurrence relation of these Stirling numbers. So the key observation is that this guy here is a polynomial in D of degree 2k. I think this is already, a good exercise for students to figure that out. And actually there are no closed formulas for the Stirling numbers. So the best you can say is this recurrence relation. So basically, what I like to suggest is that let's take these Stirling numbers as atoms or basic blocks and just introduce this notation, and I'm interested in formulas in which I can use the Stirling numbers. So it turns out that these coefficients here in the theorem, what we claim that they are polynomials, are combinations of arithmetic specializations of monomial symmetric polynomials. And I decided not to show you the exact formula because it's super complicated, but the structure itself is not very complicated. You collect different coefficients of this polynomial P and you multiply it with these arithmetic specializations. And since the monomial symmetric polynomials can be expressed in terms of the elementary symmetric polynomials, then you can immediately see an expression in Stirling numbers. Okay, so this is the general theory, which sounds like something from the 19th century, but we haven't found any sign of it, so we just developed it. Now, we are interested mainly in one example, this Paul de Cn. And it turns out that the theory implies the following, that the leading term of the kth Chern class is a power of the, well, here it's written E1, but E1 is the same as C1, of course. Okay, so you take the kth power of this guy, and you can see that the degree of this polynomial is d to the n times, the degree is n times k. Okay. Okay, so what we are mainly interested is the case when n is equal to 2, then the degree is 2k. Okay, so this result is far from trivial. In particular, it shows that if I use the basis of elementary symmetric polynomials, then most of the coefficients are 0. So many coefficients have lower degree. And I will get back to this in a moment. Actually, I will get back to this now. Okay, so when I use this basis of elementary symmetric polynomials, then I would like to understand what is the coefficient of this product. Oops. Okay, and it turns out that the degree, well, the trivial estimate would be uh, the sum of 2i times ai. Sorry, not n times ai. Okay, maybe I should write it down. Trivial estimate. What am I saying? I n times ai. Yes. And the conjecture is that this is exactly the degree. Now, uh, this, I think this statement, uh, which in itself has no applications whatsoever, uh, shows that this is a complicated calculation. Such an answer cannot be expected from a simple calculation. And in fact, it's a manipulation of maybe 5 pages to get this result. But maybe I have two more topics to talk about. One is that even these very simple stuff of calculating the total Chern class of Paul D has enumerative applications. So it's connected to the theory of Fano varieties, Fano schemes of tangent spaces. Um, if I take these strange hypersurfaces which shouldn't have an R plane in it, then I get the subvariety which contains R planes. So one way to think of this that in this dimension, the Fano scheme should be empty, at least in the generic case. So these are non-generic hypersurfaces. And I call them Manival varieties because he started to study them. And he noticed that the degree of these Manival varieties is a polynomial, but his comment was based on some calculations. And and it turned out that his guess was only valid for r equal to 2. And this is the leading term, what you can see here. So maybe I just emphasize the degree of this polynomial. So this is a non-trivial application of this funny calculation of these Chern classes. So if you want to see one example, then if you if you are looking for surfaces in the space containing a projective plane, then this degree 9 polynomial describes the degree of the Manivel variety. And notice that if you just want to calculate, it's extremely useful to have the degree of this polynomial beforehand, because it means you just have to calculate uh, enough um, enough substitutions to interpolate your polynomial. Okay, so the last topic I didn't even write down is that what happens if you want to move to motivic churn classes, when you want to calculate not the Euler characteristic, but the chi-y genus of these tangent varieties of tangent lines. And it turns out that branched coverings are not good for calculating motivic churn classes. It has to be an honest resolution. So we had to modify this branched covering to become to get a resolution, and there is a price for that. The induction gets very complex, but still manageable. And we still don't know, it's still a conjecture that this chi-y genus, the dependence of the chi-y genus is a polynomial in D. Um, because the algorithm is much more complex. What we recently figured out is that we figured out the trivial case. So what are the motivic churn classes of PolyDC? Sorry, I should show PolyDC2 somewhere. Yes. So instead of this, we are looking for the motivic churn classes. PolyDC2. And the first thing was quite scary because we realized that these are not polynomials in D. But later we figured out that that's just because the variables were not correct. So the thing is that if you use the right variables, so this is now a theorem. So maybe I stop here.
Okay, thank you very much.